Aloha class, here we go. Calculus ichi ni samban. I don't know why my video doesn't work, you guys, but it does not, but we're going to get rolling anyway. All right, here we go. So in Calculus 3, what we do is we go from 2 dimensions to 3 dimensions, right? That's the biggest thing. And obviously everything in our world is 3-dimensional, so it allows us to understand why so many things work in this world. Okay, going back to before Calc 3, pretty much a majority of the things we did were in 2 space, where we had a horizontal axis or our x-axis, and we had a vertical axis or our y-axis. Now, when we talk about 3 space, we introduce our z-axis, okay? Now, I'm going to draw the positives here. Okay, there's my positive z-axis. Okay, there's my positive x-axis. This is traditionally how we draw it, and then that's my positive y-axis. Now, we do have negative axes. Okay, I'm going to draw those in green. This would vent. Ooh, I thought it was green. It looked like it got red still on me there. So if I go to my green, this would be my negative x-axis. This would be my negative y-axis. And going down here, that'd be my negative z or z-axis. Now, when dealing in 3 dimensions, okay, in my 3 space, there's certain vocab that we want to know. Okay, the vocab we want to know is when we have when we're in 2 space, we have 4 different quadrants. Okay, in 3 space we have octants. Okay, we actually have 8 of them, 8 octants. Okay, and they're all separated by our 3 main planes. Our xy plane. Okay, that would be z being 0. Hopefully you can imagine, 3-dimensionally things are tough. You have to have good imaginations and be able to see things really well. We have a YZ plane, and as expected, we have an XZ plane, okay? And like I said earlier, we end up having octants. Go ahead and take a guess. How many different octants do you think we have in 3 space? Okay, hit pause right now and see if you get it right. Boom. Unpause. It should be ocho or hachi. There are 8 total octants in 3 space, okay? All depending on what's positive, what's negative, vice versa, and all that good stuff, okay? We also have, and it stinks that my video's not working, but we have what we call the right-hand rule, okay? If you curl the fingers of your right hand, so everybody do it with me right now. It's okay, I'm curling the fingers of my right hand, okay? And then if I take my pointy finger and I use my pointy finger and I make it represent the positive x-axis, my fingers go out where the positive y-axis are, and my thumb jets up in the positive z-axis. And so if you use your right-hand rule, then that's how you know where your positive x is in relationship to your positive y with your positive z. Okay? All right, now the question next is can we graph these dudes? Okay, so that right-hand rule you're going to see, we're going to mention that often in class, and it ends up being very important as we move on. Okay, here we go. Example 1, can you graph? Well, believe it or not, we can, and be very cautious and careful when you're graphing these. Okay, we have our positive z, we have our positive x, and we have our positive y-axis, okay? And I think the best way to do these is we want to draw lines that are parallel as we kind of venture off. Going back to 2 space, it's easy to draw just vertical and horizontal lines. Here we want to be a little bit more parallel to other axes, okay? So if it's 2, 3, 4, okay, it means I'm going to go out a positive 2 in the x-axis direction. And when I do that, I'm going to equally space these out, but if you notice, I'm going to make it parallel to the y-axis there, okay? And then what I'm going to do is I'm going to go out 3 on the y. And when I go out 3 on the y, I'm going to make it parallel to the x-axis. And it's good to relate those two and stay in the xy plane first, okay? Now, if I draw very carefully, and I'm going to do this in a different color, you guys, I'm going to do it in green. I'm going to parallel, just dash these, parallel. And where they meet is where I'm at. That would be this point right here. It's not my point yet, 2, 3, 4, but that would be 2, 3, 0. Hopefully you can visualize it right there. And drawing these little tick marks parallel to one another, I think it did kind of help it out. Okay, now how the heck do I graph the z guy? Well, the z guy means we're going to go up 4. Now, if I go up 4, I'm going to make this parallel to the y. It just makes it look easier. Okay, you're obviously not going to go over here at 4. So the positive z gets a little bit tougher. Okay, I think the smartest way to do it, and that's why we start in the xy plane, is now I'm going to go up. And I'm going to go up 4 units. And you would just want to keep those increments equal 1, 2, 3, and 4. So I guess I probably should make the actual point a different color. I'll keep it red. Okay, I'll keep it red. That's my actual point right there. That is 2, 3, 4. Kind of jets off the page. It's in that first, we would call that the first octant. Okay, we do find it helpful to draw prisms. Okay, and drawing prisms kind of really helps. So I'm going to come back here, and it's kind of like, it helps for you to visualize it maybe a little bit better. Okay, but if I'm going to draw a prism here. Okay, if I keep things really good in parallel and equally spaced out, okay, you can kind of see it. Booyah! And I'm not good at drawing, you guys. Not good at all. But I think I kind of did a good job right there. I should kind of erase this, I feel like. I went up a little bit too high here. Okay? But look at that. That's a pretty cool looking prism, I should say so myself. Now, 2 is definitely tougher. So what I would love for you to challenge yourself to do right now is, can you draw 2 without my help? So pause it. Okay, this video is not going to be tremendously long today, so let's pause it and see if we end up with the same thing. Okay, hopefully you paused, and hopefully we're back here together, and hopefully we have the same answer. Okay, so you have your positive x, y, and z, but I have some negatives here. When if I have negatives, it means I'm going off in this direction. Okay, it says first on the x to go -3, so that would be parallel to the y. -1, -2, -3. Then it says to go 2 off here in the y direction, so there would be 2. I'm going to go ahead and see where these guys, different color. I think different color really does help. So if you have different colors at home, I think it could help. Let's make those guys parallel. Okay, so it's where they meet right there. But then it says I have to go -6 in the z. So if it was from the z, it would go this way, right? But I'm going to go over where we were at right there at the corner of that prism. And I'm not going to go down 6 here, but I'm going to draw something kind of equivalent, right? And I'm going to go down 6 this way. What would that look like? 1, 2, 3, 4, 5, and 6. And that's my point. And that's my point. And like we said earlier, we could kind of finish drawing this. Darn it. Remember, we wanted to use green here to draw my prism, right? Because you got that guy, and then this guy would go here, and then it would still jet out here a little bit. That guy would go down, and you could beautifully draw your prism, everything being equally spaced, right? And then booyah. Woohoo! I'm getting kind of good at this. Okay, we'll have more homework we can do in class, right? My 2024-26 Calc 3 students said they loved flipping the classroom. So we're going to give it a shot at flipping the classroom and see how it goes from there. Okay? Find the distance between the points in examples 1 and 2. So guess what? I mean, the distance formula is here. Isn't that the same distance formula we did in 2 space, but then we just extend it to 3 space? So we have the z's. It does. So what I want you to do is using the points from the previous graph, 2, 3, 4. Right, that was one of the points, 2, 3, 4. And the other point was -3, 2, -6. I want you to find the distance between those points. Once again, this is something you can do on your own. So let's go hit pause. Let's see if we get the same answer. Okay, so essentially the distance is, it doesn't matter which ones you technically subtract, as long as you keep it in the appropriate order. 2 minus -3 squared plus 3 minus 2 squared plus 4 minus -6 squared. If you do all that perfect, you get the square root of 126. Booyah, done. That's how far away they were. If you were to draw them on that last page on the same axis, you would see exactly how far they were, right? What's that? Square root of 121 is 11, so a little bit more than 11 units from each other. Okay? All right, here we go. Sphere. Okay, how about that? I don't know about you, but that looks almost identical to the, if I get rid of the 3 space, the z's, that's a circle. Okay, so if I extend it to 3 space, hey, very, very cool. I'm dealing with a sphere. Okay, and it asked me in example 4, write the equation of the sphere with a diameter having endpoints. Okay, so I have a sphere. You don't have to technically draw this. You could if you wanted to, if you want to get a little cray-cray. Okay, but I'm going to go ahead and those are the endpoints, but it's the diameter. Okay, so you have a diameter. I'm not going to technically draw this in 3 space, but that's my diameter, and I need to know the radius. Well, okay, the radius is just, let me think here. Hopefully you're pausing and thinking of this yourself. How would you find the radius, you guys? Well, the radius is half of that. Well, in order to find half of that, it just would be the middle. So if it's just the middle, what would that be, class? Oh, yeah, that would just be the midpoint. Well, how do I find the midpoint? So let's go ahead and find the center first. What the heck would the center be? Well, midpoint, well, I bet you it's the same midpoint formula as it is if we were in 2 space. And how would we do that? Well, we would simply add the x's and divide by 2. We would add the y's and divide by 2. We would add the z's, the z's, and we would divide by 2. Boom, there is my center. So I'm done if I just know what the radius is. Well, what the heck? How do I find out what the radius is? Well, the radius would be the distance, right? The distance. Well, what the heck would the distance be? Well, let's think about this, right? Actually, I could just find the d here. Okay, I'm going to call that my distance. R is equal to d. And to find that distance, it would just be from your center point to this guy right here. And so if I did that, I would just subtract the 2. So it'd simply be the square root of negative 1/2 minus 0 squared plus 2 minus 2 squared plus 2 minus 3 squared. 2 minus 3 squared would be Ichiban squared, correct? So if I do all of that correctly, what do we get? The square root of 1/4 plus 1. That would be equal to the square root of 5/4. Okay. We're rolling. And then it said to write the equation. Well, the equation's up there for me. I needed to know the center because x naught, y naught, z naught is the center, right? Just kind of like when we did circles. Okay, so it'd simply be x minus negative 1/2, which would end up being plus squared, plus y minus y naught squared, plus z minus, or z minus, I just like z, it just sounds cool, z squared, and that is equal to the radius squared, which would be 5/4. Okay, hopefully that makes sense. I feel like it wasn't too bad. Like anything we do, you should try things on your own. Okay, it really helps for these videos to really make sense. All right, find the center and radius of the sphere. Oh, I don't know about you, but that should hopefully immediately kind of be light bulb. I know it is for me because I remember doing circles, and when we did conic sections back in Algebra 2 and a little bit in Honors Pre-Calc, that we had to complete the square. Right? Why complete the square? Because I want to know what the center is and I want to know what the radius is. And if I complete the square and put it in standard form, I am good to go. Yes, sir. Okay, so let's go ahead and do that. Do you remember how we used to complete the square? If you do, hit pause. Let's see if you can get it on your own. If not, we'll do it now and we'll practice it in class. Okay, but remember, we put the x families together. Okay, I'm going to put a blank there because I want to complete the square. I'm going to put the y families together. Put a blank there because I have to complete the square. I got to get the perfect square that I can factor. And then I'm going to put the z family together. And then I'm going to do a plus blank because I got to add something there. Once again, why? Well, because I need to complete the square and get a perfect square. And then I'm going to get rid of everything else. But remember, okay, you need to balance out your equation. You're allowed to change what it looks like. You can't change what it actually is. So I'm going to add 2 more blanks here. And if I add the blank here and add the same number there, then they actually cancel themselves out. So I'm not really changing it, just the way it looks. Remember, how do we complete the square? You take half of the middle dude and you square it. You take half of the middle guy and then you square it. You take half of the middle guy and then you square it. And then I got to add a 1, a 4, and a 16 there. Ooh, that gives me a 4 there. Let's go ahead and factor. They're perfect squares. That's why it's called completing the square. Duh. Oh my gosh. Does that do everything for me? It does. That means the center of this sphere is 1, 2, negative 4. And the radius of this particular sphere is the square root of 4, which is Niban. All right, important theorem. Okay, if you ever have an equation that is in this form, it is a sphere, a point, or it has no graph. Well, how am I supposed to know? Well, it would be a sphere if you have your x squared, y squared, and z squared. You would have a point only in the situation if r is equal to 0. Doesn't that make sense? It would just be a point. If r is equal to 0, you wouldn't have a radius. Duh. But you'd have your center. Okay, and what about when would it have no graph? What would have no graph if and only if? Yeah, we should do that. If and only if. I like if. If, right? That's if and only if. Fancy little shorthand for really high mathematicians. So it has no graph if it's of that form. If and only if, okay, r is less than 0. Okay, obviously you can't have anything if that's the case, right? Just like going back to old time circle days. Okay? All right, here we go. A couple more pages. Several more pages. Define cylindrical surfaces. Okay, can you graph y equals 3 in 3 space? Well, that's the fancy 3 space. Do you guys remember what this is? That would be 2 space. I think a lot of these things when we're exploring, and we're going to be exploring quite a bit in class, it's helpful first to think of it in 2 space. And if I were to think about y equals 3 in 2 space, it'd be 1, 2, 3, it'd be that horizontal line. Okay? Now what I would love for you to do is kind of pause. Challenge yourself here. What do you think it would look like in 3 space? Where I have a z, an x, and a y. Go ahead and take a stab. What do you guys think it would look like? Okay, what do you think y equals 3 would look like? Hopefully you're going to hit pause and then unpause. I'm going to go out here, just like I did in 2 space, right? That's why thinking of 2 space can help you with 3 space. I'm going to go out here, and I'm going to go ahead and draw what it would look like. It would be a line, boom. But then this line, y is always 3. That means x could be anything. That means z could be anything. Well, if x could be anything and z anything, does it make sense that this would be like a plane? And we draw things like parallel and we shade it in. And you obviously can't draw this plane because it goes on infinitely. And we can't draw like arrows going everywhere this way, arrows going, there'd be just too many arrows. So it's helpful to kind of sketch what these things look like and then just write some important information, okay? In 3 space, y equals 3 represents, okay, a vertical plane, right? A vertical plane is going up and down. A vertical plane that is parallel to the which plane? It's parallel to the xz plane. So this will help you to know what some of the other, what z equals 3 look like. What's x equals 3 look like? And it is 3 units, 3 units to the right of the xz plane, Because the xz plane is kind of like that glass. It's kind of like your origin, right? But what's the origin of 3 space? So that's what I'm kind of referring to there. Okay? I'm going to erase some of that right now so that we have a little bit more room. What do you think y equals x looks like? All right? Come on. Please do me a favor and try something on your own. It's awesome when you're able to think of these on your own. And some of you guys are going to really struggle. And some of you guys have always had really good minds of this stuff. So let's see who's like killing it, who's rocking it, and then who we just gotta work a little bit harder to make sure we're understanding, because this is the foundation of our entire semester, you guys. Okay? All right, here we go. Now I'm gonna think in 2 space what it would look like. 2 space, y equals x, 1, 1, right? Boom, boom. Okay. Kind of cuts through it there. All right, maybe that will help me out a little bit. I sure hope it does. We have a z, we have an x, and we have a y. Okay, remember, you should be hitting pause. What the heck would y equals x look like? Maybe I'll draw it a different color here. Boom. We'll draw this one in green. Well, it looks like z could be anything. So z could be anything. Okay. But when x is 1, y is 1. 2, 2, 3, 3, right? Kind of jetting out in both directions. So it kind of looks like that, right? If I it will go back out in that direction too. Okay, but z could be anything. So if z become anything, then it means it would jet, it would jet straight up, kind of parallel, and we shade it in. Okay, can you kind of visualize it? I think I can. Okay, my drawing isn't the best in the world, but let's make a little note. So in 3 space, y equals to x. Once again, it looks like it's vertical, is a vertical, heck yeah, it goes straight up and down, doesn't it? Is a vertical plane, okay, that intersects. Okay, it looks like it always is intersecting, so it intersects the xy plane, and it does. It intersects that plane in the line, y equals x, which is the same as z is equal to 0. So that's kind of where it cuts it. Okay, and it cuts it through going infinitely in both directions. I don't know about you, but kind of cool. Kind of cool to think about that and see what it looks like a little bit. Okay, here we go. Just two last examples. Boy, come on now. Challenge yourself. What the heck would that look like? Kind of circular, but we're in 3 space. So maybe a whole bunch of circles? Man, I hope you guys are hitting pause. Just are going to learn so much more if you're going to hit pause. And I'm actually going to hit pause in a second because Desmos has a really, really cool 3D graphing calculator. Gosh darn it. Okay, Desmos has a really cool one, but I hope you're going to try it real quickly on your own here. What the heck would that look like? You know what I like to do when I'm not sure? It's just like what I taught you guys in pre-calc. If you had me in pre-calc, I like to put zeros in. Obviously, there's no y. So y could be anything. What the what? Well, I'm going to put a 0 in for x. And if I put a 0 in for x, that means z could be plus or minus 1. Well, if I put a 0 in for x, that means this is on the graph, that's on the graph, and this guy down here is on the graph. Okay. Well, if I put a 0 in for z, that means positive 1 is on the graph, and negative 1 is on the graph. And that's going to be a circle. That's going to be a circle. And then guess what? Y doesn't matter what y is. Doesn't matter what y is. So guess what? You're getting all these circles that go on infinitely. Kind of nuts. Kind of really, really cool. So in 3 space, x squared plus z squared, which is equal to 1, is a cylinder. With a radius that's equal to 1 that is parallel to the y-axis. All right, I'm going to graph these with Desmos last. Okay, so I can kind of help you see what that stuff is. Okay, actually, yeah, let's get this last one done. Okay, describe this graph. Just describe it. Doesn't even ask you to graph it. Okay, let's go ahead and do that real quickly. Okay, I'm going to come over here. Let's see. And then I'm going to show you guys. It's Desmos. Okay, so you can go to Desmos. Please use this website to explore. Okay, it's really, really helpful. Okay, to explore. Oh no, are they charging? 3D. 3D Desmos. Look at that. So cool. I like to do it the way we do it in class. Is that positive x? Oh my gosh, you have to like hit the button. I think that's positive x, positive y, and positive z going up. Yep, I think we're good. Okay, and then I'm going to type in z squared. Okay, z squared, use a little caret to get the exponent, plus x squared plus z squared, use a little caret, and that equal to 1. Check this out. Booyah! Isn't that so cool? And like you can move this dude. But it's just such a great website, you guys, to understand what's going on. Okay, it's right. I don't know about you, but I love this Desmos, and everybody can use it. It's free and everything. All right, describe the graph of x squared plus y squared plus z squared, but it has to be greater than 1 and less than 4. Okay, so think about it really quickly, and let's see if your thoughts were correct. All right, So what the heck would this look like? Well, I think it would be as spheres, but it would be spheres. Ooh, let's write some stuff down. In 3 space, okay? 1 is less than or equal to x squared plus y squared plus z squared, which is less than or equal to 4, represents, I would say probably it represents spheres, but it's spheres that are centered around the origin, and they have radii from 1, square root of 1, to square root of 4. So from 1 to 2. Okay? I know I explained that all. I didn't write it all, but that's what I got. Okay, what if z was less than or equal to 0? Well, if z had to be less than or equal to 0, it wouldn't be entire spheres. It would just be like hemispheres. Kind of makes sense? Yeah, so that's all you would have to do there. I mean, for what that was asking. Now, could I draw what this kind of looked like? Maybe. Let's go ahead and put it. Let's add a y squared. I know. Look how much that thing changed, right? But then put a plus sign. See, so then you have a sphere. Okay, that would be of a radius of 1. So it's got to be bigger than that. So if it's bigger than that, ooh, let me do this. It's kind of cool. I think you can pick different colors too and everything, you guys. Boom. Look at that. Ooh, 4. Shoot. See, you can kind of see it. Boom, boom. So it's that area of the region between that. Like, how are you supposed to draw that? You can't draw it. That's why the problem specifically said to explain it. And that is our first lesson of the Calc 3 Loyola year. Section 12.1, 3-dimensional coordinate systems. We'll work on the homework in class. Aloha.